In category theory, a branch of mathematics, group objects are certain generalizations of groups which are built on more complicated structures than sets. A typical example of a group object is a topological group, a group whose underlying set is a topological space such that the group operations are continuous. Definition. Formally, we start with a category C with finite products. A group object in C is an object G of C together with morphisms M, G times GG, E, 1G, INV, GG, such that the following properties are satisfied. M is associative, i.e., M equals M as morphisms G times GG, and where e.g., M times IDG, G times GG times G. Here we identify G times in a canonical manner with times G. E is a two-sided unit of M, i.e., M equals P1, where P1, G times 1G is the canonical projection, and M equals P2, where P2, 1 times GG is the canonical projection. INV is a two-sided inverse for EM, i.e., if D, GG times G is the diagonal map, and EG, GG is the composition of the unique morphism G1 with E, then MD equals EG and MD equals EG. Note that this is stated in terms of maps. Product and inverse must be maps in the category, and without any reference to underlying elements of group. Categories in general do not have elements to their objects. Another way to state the above is to say G is a group object in a category C if for every object X in C, there is a group structure on the morphisms HOM from X to G such that the association of X to HOM is a functor from C to the category of groups. Examples. Each set G for which a group structure can be defined can be considered a group object in the category of sets. The map M is the group operation, the map E picks out the identity element U of G, and the map INV assigns to every group element its inverse, e.g., GG is the map that sends every element of G to the identity element. A topological group is a group object in the category of topological spaces with continuous functions. A Lie group is a group object in the category of smooth manifolds with smooth maps. A Lie supergroup is a group object in the category of supermanifolds. An algebraic group is a group object in the category of algebraic varieties. In modern algebraic geometry, one considers the more general group schemes, group objects in the category of schemes. A localic group is a group object in the category of locales. The group objects in the category of groups are the abelian groups. The reason for this is that, if INV is assumed to be a homomorphism, then G must be abelian. More precisely, if A is an abelian group and we denote by M the group multiplication of A, by E the inclusion of the identity element, and by INV the inversion operation on A, then is a group object in the category of groups. Conversely, if is a group object in one of those categories, then M necessarily coincides with the given operation on A. E is the inclusion of the given identity element on A, INV is the inversion operation, and A with the given operation is an abelian group. See also Ekman-Hilton argument. Given a category C with finite coproducts, a cogroup object is an object G of C together with a comultiplication M, GGG, a co-identity E, G0, and a coinversion INV, GG, which satisfy the dual versions of the axioms for group objects. Here 0 is the initial object of C. Cogroup objects occur naturally in algebraic topology. Group theory generalized. Much of group theory can be formulated in the context of the more general group objects. The notions of group homomorphism, subgroup, normal subgroup and the isomorphism theorems are typical examples. However, results of group theory that talk about individual elements, or the order of specific elements or subgroups, normally cannot be generalized to group objects in a straightforward manner.